Alright, we're going to get going today. We'll have a little bit shorter of a class period because I have to end early for course evaluations, as you all know, and that presumably explains the higher than normal attendance today. So just to be clear on a few things, the first frequently asked question that I've gotten recently is what exactly is the cutoff for the third midterm? You know, which material is on the third midterm versus which stuff is not. So everything we covered before today, including the last Monday's class, will be on or could be on the third midterm. Is fair game. This stuff that we covered today and anything beyond today, of course, will not be until the final exam. So that's kind of the cutoff. The end of last lecture was basically the end of what could be on the midterm that's coming up. Now, on the topic of that midterm exam, we're going to have, as a final reminder, the review session for that will be this coming Friday. So that's April 20th, and that's going to be at 1 p.m. in this room. Alright, so again, it's optional if you come to that, of course, but it will be recorded and posted on YouTube if you're not available to come or want to revisit it afterwards. And then in terms of what's left after that, we're getting close to the end, as you probably are aware. We have 3 more classes after today, which probably fills you with some combination of terror and happiness, depending on how you think about it. And so we have 3 classes left after today. Next week, on Monday and Wednesday, we're going to finish all of the course material is my plan to get through all of Chapter 9, which means that the final exam review we're going to have divided up into 2 parts. So part 1 is going to be Friday, April 27th, and I'll give you more reminders of this because it's a little bit down the road. But so that's going to be our normal Friday exam review time slot. And we'll go through. I'll have to figure out exactly how I want to break it up. Probably half or a little bit more than half of the final exam we'll review on that Friday. And then the last day of class we'll do the second half of the review. So the very last day that we meet for this class, we'll be also doing the final exam review and nothing new on that day. Okay, so that's kind of an idea of where we're going in the next week and a half or 2 weeks before we wrap this up all together. All right, so what we're going to cover today, which is going to be structures of ionic compounds. We talked last time about in very much detail the structures of metal solids, metallic solids, and then we did a little bit on some of the structures and properties of covalent, what we call network solids. And today we're going to talk about another class of compounds, ionic compounds. So we already know a lot about ionic compounds from various things that we've done in this course, mainly in chapters, I guess it was 3 and 6 that we talked a lot about ionic compounds. And as we're already aware of, the reason that ionic compounds form in the first place, and this is that whole topic of lattice enthalpy that we've been dealing with even more recently than that, the reason that they form is that you have forces of attraction between the oppositely charged ions. Okay? So that's sort of what holds these compounds together. We know that from calculating lattice enthalpy that's usually a very large energy of interaction between those that's responsible for the formation of ionic compounds and their crystalline structures. So these are Coulombic forces of attraction, very strong forces between oppositely charged ions. So what we're going to learn about today are the precise structures of ionic compounds. So how exactly do the cations and the anions arrange themselves when we have a crystalline ionic compound? And the whole idea here is that the structures that we observe, we're going to just sort of talk about them, their features and what they look like, but we're not going to get into too much details of how they form. But the whole idea is that the structures that we observe, they're going to maximize the attractions between the ions, while also minimizing repulsions between the like-charged ions. So ideally what we want to do is if we have a positive ion in our ionic compound, we want to surround that with as many negative charges as possible to maximize the forces of attraction. However, if you go too crazy with that, you're going to start putting those negative ions too close to each other and they're going to repel each other. So as we'll see, the exact structure that forms depends on the relative sizes of the ions. How close can we get them to each other? How many of one ion can we surround with the other to be able to sort of maximize these interactions? So the way we form these structures then is in a ionic compound we're going to have two ions, and barring a really neat coincidence, they're going to have slightly different ionic radii. They're not going to be exactly the same size, of course. So you're going to have one ion that's larger, one ion that's smaller. Usually the larger ion is the negative charge. So as we know, when you add electrons to something, it becomes negatively charged, although it is possible to have an ionic compound where the positive charge is the larger ionic radius. So there's variations here, but usually the negative ions. And what we're going to do with these larger ions is we're going to put them into one of those cubic structures that we learned about last time. So these larger ions, usually the negative ones, they're going to occupy one of the common packing arrangements that we learned that we applied to the structures of metals last time. Now there's a lot of ionic structures out there in the world, so we're only going to talk about a small subset of them. The ones that we'll see, these larger ions, that usually the negative charges, are going to occupy either a primitive cubic lattice, which means we're going to put one negatively charged ion at every corner of the cube, or alternatively we would see them in the face-centered cubic arrangement where one negatively charged ion occupies all the corners and all the faces, as we saw for the FCC or cubic close pack structure. So our negatively charged ions are going to fall into those positions, that one of the ones that we learned last time, and we're going to primarily just talk about these two that in the context of ionic compounds. There's a couple other from metals that we saw, but just these two for ionic compounds. And then what we're going to do is we're going to take the smaller ions. Again, these are usually the positively charged ones in the structure, but whatever ion is smaller will go into the holes in the structure. So we're going to have different gaps in the structure, and we're going to fill those in with the oppositely charged ion. And what we're going to learn today is to predict. We're going to define different holes in these structures, different locations where oppositely charged ions can be placed into, and then we're going to learn to predict which of those holes are occupied, how many of those holes are occupied, and so on. All right, so the observed structure and which holes are occupied that's going to depend on the relative sizes of the ions. So as we'll see, if the ions are really close in size, there's going to be one structure that's preferred. If the ions are a little bit different in size, there's another structure. And if the ions are way different in size, there's going to be another structure type. And sort of the location of the ions in the structure is going to depend on their relative size, is what we're going to sort of get into today. So let's talk about then the types of holes that we have in these cubic structures. So we're going to start with one of these cubic structures that we already learned last time, either face-centered cubic or primitive cubic, and we're going to put holes into them where the opposite ions are going to go. So let's start with the first type of hole. Is called a tetrahedral hole. Now, if you're thinking about it in terms of a layered structure, the tetrahedral hole would fall into one of these dimples in the close packed layers. Remember we said these face-centered cubic arrangements are formed by taking close packed layers of atoms and then stacking them up on each other in different ways. And so in each layer you're going to have a little dimple that formed in between three close packed atoms. And if you put another ion right in that little dimple, we call that a tetrahedral hole. So if you're thinking about it in terms of the layered structure, it's in one of these dimples in a closed packed layer. But I think the easier way to think about it is where they're located once we draw the cubic unit cell. So there's going to be one in each corner region of the unit cell in a cubic close packed or face-centered cubic structure. All right, these are perhaps the most difficult to visualize in of the holes. So we'll start with the hard one first. And so what you have is, what I'm showing here is these gray spheres represent the face-centered cubic structure that we learned about last time. So imagine that's one of your ions. And then in each corner of the larger cube, so we're going to highlight 4 of these in purple here, you have 3 atoms on the faces and 1 in the corner. And in between all 4 of those is going to be a little hole here. And so you're going to have one of those holes in each corner. Another way to think about this is, imagine that you draw a smaller cube inside of your larger cube. Each corner of that smaller cube would be what we call a tetrahedral hole. So it's located in the corner region, but it's completely inside the unit cell. It's not on one of the edges or on the sides. And it's surrounded by, equidistantly by 4 atoms, 3 on faces, 1 in the corner that are nearest to it. So these 4 purple ones that I'm showing. Okay? And we call it a tetrahedral hole because, as we learned earlier in the course, tetrahedral means 4 coordinated. That means it has 4 bonds to it. And as you can see, this ion here interacts with 4 nearby ions of the opposite charge. So we call it a tetrahedral hole, but it's located completely inside of the cube. Okay? So let's talk about then the relative size of these holes, because what we're going to do then is we're going to determine the size of the hole relative to the radius of the larger ion, and then depending on those ratios, it's going to predict whether this hole gets filled or some other hole gets filled. So let's talk about the limiting radius for a tetrahedral hole. So one thing we learned last time is that if you have a face-centered cubic structure, the side length A, so that's the distance from one corner to the other along the side of the cube, that distance is given by 2 times square root of 2 times the radius. Where in this case we're going to use capital R to denote the radius of the larger ion, which is located on the FCC positions. So that's something we learned last time. We derived it geometrically. But that's the distance A along the side. And then let's also think about then the distance along the diagonal here. So we talked about that last time too, distance from one corner all the way to the opposite one. So the diagonal of the entire cube itself is given by the side length A times square root of 3. And let's consider, in this case, let's do half of the diagonal, maybe a little bit easier to think about this. Let's go from one corner to the center of the cube, so halfway along that diagonal. So we're going to do 1/2 times the diameter of the cube is equal to a radical 3 over 2, which in terms of the larger radius r would be then radical 2 times radical 3 times r. So we're going to make this substitution. We're going to replace a with radical 2 times r, and then that goes into here and get this substitution. So that's 1/2 times the the diagonal of the cube. And then what we see is, as we go along this diagonal, we start here in the bottom corner, we go through 1 atomic radius or ionic radius of the larger ion. We go through the tetrahedral hole where the opposite ion is located, so we go through 2 times the radius of the ion that's there. And then to get to this corner, because it's a symmetric cube, we have to go through another radius of the larger ion in the center. So what you get then is that as we traverse across the diagonal from the corner to the center, what we get is 2 times the big radius is the distance plus 2 times the smaller radius, which is the radius of the ion that's in the tetrahedral hole. So you have to go through the tetrahedral hole, and you have to also go through 2 corner atoms, or the equivalent of 2 corner atoms as you make that. So then what we can solve for is we can rearrange everything, and we get that square root of 2 times square root of 3 divided by 2 is times the big radius is equal to the sum of the 2. And then solving for that, the small radius r, which is the radius of the ion that can fit into this tetrahedral hole, is going to be given by radical 2 radical 3 over 2 minus 1 times big R. And the number that comes out of this, which is the important part, again, we're not going to concern ourselves with geometry too much in this course, is going to be 0.225. All right? So that means the small radius, the radius of the smaller ion that can fit into that tetrahedral hole, will ideally be 0.225 times the bigger radius if these larger ions are packed completely close together, as they can be in these structures. So we see that this is the relative sizes then of the two holes. So if you have an ion of radius big R on each corner and each face, we can fit an ion that's 0.225 times that into this tetrahedral hole without having to expand the structure at all. So that's the relative sizes of the tetrahedral hole relative to the other ion that's in the crystal structure. The next type of holes, which are a little bit easier to visualize, are called octahedral holes. And so what these are located, if we think about the layers, they're between two sets of three. So they're a little bit different location. They're between two sets of three spheres and adjacent CCP layers. But once again, I think the easier way to think about it is, where are these holes located once we draw the face-centered cubic structure? So we have a face-centered cubic arrangement of one ion. The octahedral holes, which is one of the other positions that a second ion can go, there's going to be one along each edge. And there's going to be one in the center. All right, so that's what we're showing here. We have a cubic unit cell drawn. The red spheres, the red ions as we're drawing them, occupy the face-centered cubic positions. So there's one in each corner, one in each face of the cube. And then the octahedral holes, which are labeled with these little white and black circles here, those octahedral holes, there's one on each edge of the cube in between the two red ones, and there's one directly in the center. So that's the location of the octahedral holes. Okay? And the reason we call it octahedral holes is that if you focus on this one in the center here, you can see that it's surrounded by 6 of the other ion, the ones that are all on the faces in this orientation. So we call it octahedral hole because the geometry at that octahedral hole is going to be octahedral. There's 6 things surrounding it in that type of geometry. All right, so that's what the octahedral holes look like. Let's talk about then the relative size. Again, the derivation is a little bit annoying, but we can do it. So if we determine the relative size, this time it's a little bit easier because as we go along one edge of our cube here, we said that the distance along that edge is given by 2 times the square root of 2 times the bigger radius. We derived that last time. And then as we go along the edge, we also pass through one of our octahedral holes here that's along the edge. So as we go from here to here, we have one radius of the bigger ion, 2 times the radius of the smaller, and then another radius of the bigger ion to take us to that corner. And so that means this 2 radical 2r is equivalent to 2 times big R plus 2 times little r as we go from along the side of one of the sides of our cube. And so then we just rearrange this. Radical 2r is equal to the sum of the 2 radii, or that the small radius is equal to square root of 2 minus 1 times the larger, or 0.414. So what we see then is that the octahedral hole is larger than a tetrahedral hole. We saw that the tetrahedral holes were 0.225 times the radius of the larger ion. These ones are 0.414 times that radius. All right, so there's 2 different holes that we've learned about now in the cubic close-packed or face-centered cubic structure. The tetrahedral holes, which are located in each corner, are the smaller of the 2 holes. The octahedral holes, which are on the edges and in the center, are slightly larger than that. Okay, so any questions on the holes that we see in a face-centered cubic structure? All right, the very last one then is going to be the cubic hole, which I think is the simplest one. So in a cubic hole, what we're starting with is just a simple cubic structure, meaning we just have atoms on the corners now, ions on the corners, and the cubic hole is located right in the center of that simple cubic structure. So it's the center of a simple cubic structure. And that's exactly what this is showing here. You have atoms in each corner, ions in each corner, and then you have another one in the center. So this is a lot like body-centered cubic, which we learned last time. The difference here is that we're talking about structure of ionic compounds where ions of one charge would be on the corners, ions of the opposite charge would be in the center. In a body-centered cubic metallic structure, it's all of the same atoms that are occupying the corners and the center. So it looks a lot like that, but keep in mind that when we're talking about ionic compounds, it's 2 different ions, one on the corner, one in the center. Okay? So that's where the hole is located. And this one is also fairly easy to derive. So what we saw for the simple cubic structure was that the length of the side is just given by 2 times the radius. So as we go along the side of a simple cubic structure, all we have are the radii of the 2 ions that are at each corner. So that's the length of a side A. The cube diagonal, as we've already seen today, is equal to A times the square root of 3. And as we go along the cube diagonal in this structure, we pass through the radius of the larger ion in each corner, so 2 times the larger radius. And we pass through the center position, the whole diameter of the center ion, so it's going to be also plus 2 times the smaller radius as we traverse from corner to corner. We go through 2 big radii and 2 small radii. So again, we have this relationship. We rearrange things a little bit. So we substitute 2r in for A here, and we get 2r radical 3 is equal to 2 times big R plus 2 times small r. Divide by 2. Solve for small r, and we get radical 3 minus 1, which is 0.732 times big R. So that means that this cubic hole here is even larger than the other 2. So it's a different structure that we're starting with. Here we're starting with a simple cube instead of a face-centered cube, but the size of the hole that we can fill in this is even larger than we saw for octahedral holes. All right, so there's 3 different holes, and they're given by different relative sizes as we see. All right, so any questions on the holes themselves? All right, the next thing that we want to talk about then is how we count the holes. So an important thing to think about when we're talking about the formulas and the structures of ionic compounds is how many of each ion do we have present in the crystal, and what holes need to be filled to give the correct ratio. So we already know that if you have an ionic compound, the positive and the negative charges have to balance each other, they have to cancel. So we need to figure out how many of each of these holes there are to know how many of those get filled when we're building an ionic compound with these types of structures. So let's talk about the 3 different types of holes. So tetrahedral holes, as I said, all 8 of them, this diagram shows all 8 of them. All 8 of the tetrahedral holes are inside of the cube. They're located inside of each corner on a smaller cube that's sort of transcribed inside the larger cube. And so all 8 are inside. Which means that if we occupy all 8 tetrahedral holes, there would be 8 ions inside of that type in the crystal. So a maximum of 8 tetrahedral holes. Again, saying that if each one of those has an ion, there will be 8 of that ion in the unit cell because all 8 of those are completely inside the unit cell. Okay, so all of those are inside. That means we count them as 8. For the rest of these, we have to remember the counting rules that we learned last time, especially for octahedral holes. So as we said, in octahedral holes, you have all of the edges include an octahedral hole. So there's 12 edges on a cube. And what did we say? How do we count the edge positions? We didn't deal with. We talked about this at the very beginning of last time. So what is an edge counted? Is it a full? Is it a half? A quarter? An eighth? A fourth? Right. So this edge position is shared by 4 adjacent unit cells. So each edge counts as 1/4 of an atom or an ion. And then we also said that one of the octahedral holes is directly in the center of the face-centered cube. So in the center position, we have 1 additional octahedral hole, and we count that as a full ion because it's not shared by any other adjacent unit cells. Remember, anything that's in the body center counts as a full atom or ion. And so then what we end up with is this total of 4 octahedral holes. So if all of the octahedral holes are filled, you would have 4 of that ion in your ionic compound structure. Okay? So that's how the octahedral holes work. And then finally, for cubic holes, we said that that was the last one we did. It's just located right at the center of the cube. So we have 1 center position completely inside the unit cell, so that means there's 1 cubic hole. All right, the cubic hole is not shared by any adjacent unit cell because it's directly in the center, completely enclosed within the unit cell of the compound. All right, so that's how we count the cubic holes. And again, the types of problems we're going to ask you are not going to be so much to be able to memorize all the different ionic compounds and what their structures are, but to be able to answer questions about the different holes and things and how many there are and be able to count them correctly and stuff of that sort. So what I'll give you now is a summary of the holes. I think I accidentally put this slide in here twice, so we'll just do it once, but this is a good time to do it. So we have, again, 3 different types of holes that we fill when we make ionic compounds: tetrahedral, octahedral, and cubic. As we just saw, the number per unit cell is different for each of these. 8 tetrahedral holes, 4 octahedral holes, and 1 cubic hole in net per unit cell. Now we talked about the relative sizes, so we derived all of these. And what we said was that if you have a tetrahedral hole, the size that we derived was 0.225 times the bigger radius r. So that was sort of the ideal size. Now this size that we derived sort of assumes that we're not expanding the structure at all. It assumes that the negatively charged ions, or the larger ions, are still in the close packed arrangement. They're still exactly in the center, in the positions that you would see for a cubic close packed. For octahedral holes, we saw that the limiting size was 0.414, and then we saw that for cubic holes, the limiting size was 0.732. Now what happens then is, to determine which of the holes are filled, it's going to be the numbers that lie in between these. So if you have a smaller ion that has a radius of 0.225 times the larger, all the way up to 0.414, in any of that range, you're going to occupy the tetrahedral holes. So what this means is that the structure can expand a little bit to accommodate even larger ions than 0.225 R. So if the radius of the smaller ion is greater than 0.225 times the radius of the larger ion, you can expand the structure out, and until it gets to 0.414 times the radius of the larger ion, you're going to fill tetrahedral holes. As soon as it crosses this threshold, you're going to start filling octahedral holes instead, and then this is going to be then bounded by those two numbers. So an octahedral hole we filled anytime the radius of the smaller ion lies between 0.414 and 0.732 times the radius of the larger ion. So again, this is the minimum radius where you'll start filling octahedral holes. You can then expand the structure to some extent until you get to this limiting value. And then anytime the radii of the two are closer together than 0.732 times, anytime it's bigger than that, you're going to fill the cubic holes. Okay? And so this again is the ratio of the radii of the smaller ion to the larger ion, and these are the limits then of each of the holes that will tell you which of the holes get filled. And then finally, it's important to also remember which unit cell the parent ion or the larger ion resides in. So the tetrahedral holes and the octahedral holes occur in a face-centered cubic structure. The cubic hole, as we saw, is formed when we have a primitive cubic arrangement of one of the ions. All right, so 2 different parent structures. Within the FCC structure, we have 2 different holes that can be filled, which is determined by the relative ratio of the radii. And then the cubic holes go into the primitive cubic structure when the radius is even larger. All right? All right, any questions? So let's do a few examples of ionic structures to see exactly how this works. All right, so let's talk about perhaps the world's most common ionic compound, or at least the one that people are most familiar with, which is sodium chloride, NaCl. So ionic solids are created by filling holes in cubic close packed structures with the opposite ions. So let's talk about NaCl. So the first thing to think about when you're evaluating what type of structure you're expecting to have is, what are the ionic radii? Now, we're not going to be able to memorize ionic radii, but we should recognize that from periodic trends, the radius of sodium should be smaller than chlorine. Let's review that quickly. So the sodium ion has the same configuration as neon, has 10 electrons. The chloride ion has the same configuration as argon, has 18 electrons. So we should recognize then that chloride is going to be larger than sodium, okay, just based on periodic trends and ionic radius we talked about. Now, to know the exact structure that we get, we have to know precisely what those radii are. Just knowing that one is larger than the other doesn't tell us what structure we're going to get. But if you look at the actual numbers, which you would not have to memorize, of course, for sodium, the ionic radius is 102 picometers. So again, picometers is 10 to the minus 12 meters. It's a very common unit when we're talking about atomic and ionic radii. And the chloride ion, the ionic radius of chloride is 181. So as we see, it is quite a bit larger. Okay? So if we want to predict then what structure these two ions will form when they make a compound, we have to think about the ratio of the radii. So we take the ratio of the smaller radius, which is sodium, divided by the ratio of the larger one, which I'll abbreviate with capital R to keep the notation the same as I used before. And so the ratio of these two ionic radii is 0.56. And we see that that is in between 0.414 and 0.732. And so when that is the case, when it's between those two numbers, as we just saw, we're going to fill the octahedral holes. All right, if the radius ratio was smaller than 0.414, we would fill the tetrahedral holes. If the ratio was larger than 0.732, we would fill cubic holes, but when it's in between these two, in the middle region, we fill the octahedral holes. So what that means then is that we're going to have a face-centered cubic arrangement of chloride ions. So the ones in green are going to be chloride in the picture that I have here. So we're going to put the chloride ions in a face-centered cubic arrangement, one in each corner, one on each face of the cube. And then the orange ones, which are sodium, are going to be occupying the octahedral holes. So we see that there's an orange ion right along each edge, which is one place where you have octahedral holes. And then you have this one right here in the center. Okay, so that's where the sodium ions go. Now we have to figure out if all of the octahedral holes are filled or just some of them. So let's count and figure this out. So our chloride ions occupy a face-centered cubic lattice. So as we saw last time, when we count the number of ions or atoms that are present in a face-centered cubic lattice, we have, for the green ones, the chlorides, we have 8 that are on the corners, and those all count as 1/8 because they're shared by 8 unit cells. And then we also have 6 chloride ions that are in the faces here, and those are shared by 2 unit cells. So what this means is that in this structure, if we occupy the face-centered cubic arrangement, we're going to have 4 chloride ions. And then if we think about how many octahedral holes we have, which is in the table that I just wrote, but let's count it again to make sure we understand how that works. The sodium is going to occupy octahedral holes, and if we fill the octahedral holes, we have 12 along the edges that count as 1/4, and we have the one in the center that we count as a full one, which means we would have 4 sodium pluses if we occupied the octahedral holes. Now we know the formula of sodium chloride is NaCl, which means that all of these have to be filled. Because if we fill all of the octahedral holes, we have 4 sodiums, we have 4 chlorines, sorry, it's chlorine, 4 chlorides, which then reduces to NaCl, 1-to-1 ratio. So in order to have the correct 1-to-1 ratio of cations to anions, we have to fill every single octahedral hole in the structure. Okay? So that's how it typically works for octahedral holes, but not always. And then finally, what's the coordination number of the cation or any of the ions in the structure? So as we said, the octahedral hole, the reason we call it that is because it's surrounded by 6 other ions. So if we go to the center octahedral hole, we see that there's 1, 2, 3, 4, 5, 6 nearest neighbor ions that are on the faces. And so anytime you have an octahedral hole, the coordination number will be 6. And that's what the name octahedral tells you directly. So we already know that octahedral refers to 6 electron groups, and then by the same vein, when you have an octahedral hole filled in a crystal, 6 oppositely charged ions surround that as nearest neighbors. All right, so that's some details about the structure of sodium chloride, which again, the point of all this is not for you to memorize this structure and say, oh yeah, sodium chloride has this radius and this hole's filled, but to be able to evaluate this and understand it. We'll get some more example problems later that show us how this will work on homework and test questions. Let's do another common structure, which is cesium chloride. So cesium chloride is another alkali metal halide, but let's replace sodium with cesium. So we go from sodium chloride to cesium chloride. Cesium is farther down on the periodic table. All right, so we know that cesium is larger than sodium. And if we compare the ionic radii in this case, we saw last time that the ionic radius of chloride was 181 picometers. That's the number we gave you last time. We know that cesium is larger than sodium, so how much larger is it? The radius that we get for cesium is actually very close to that, 174 picometers. So in this case, the radius of the cation is only a little bit smaller than the radius of the anion. They're very close to each other, nearly equal. So now let's predict which holes are filled, what kind of structure that we get. Now you can see the picture there, so the cat is out of the bag, but let's try to rationalize the structure that we get. So we're going to take the radius of the smaller ion, cesium, divided by the radius of Cl-, the larger ion. This is going to be pretty darn close to 1, as we already can tell. So we divide the two numbers, That comes out to 0.96. And as we saw, if the radius of the smaller ion is greater than 0.732 times the radius of the larger, that means we have to fill the cubic holes in this structure. Okay? So anytime the radius ratio is greater than 0.732, when you divide the smaller by the larger, you have to fill the larger cubic holes, which are in the center of the simple cubic structure. All right, so we're going to fill the cubic holes. Let's think about how many of the cubic holes are filled. We're going to fill every single one, or we're going to have to skip some cubic holes throughout the structure. So in a simple cubic arrangement, which is what our ion has in this case, so again, here we have, again, green representing Cl minus, blue in the center represents the cesium. And if we have a simple cubic arrangement of our anions, of our chlorides, we have 8 corners filled that count as 1/8, so we have a total of 1 chloride ion in this structure. And then for the cubic hole, which is right in the center, as we saw, the cubic hole, we have 1, it counts as 1, so there's going to be 1 cesium plus. So that means all of them are filled again. To make sure that we maintain a 1-to-1 ratio of cations to anions. All right, because there's a net of 1 chloride, which means we have to have 1 cation. In order to have that, we have to fill every single octahedral hole. We can't fill any. We can't skip any. Okay? So we fill all of them again, and this is the structure that you get from that, as I show you here. And then if we think about the coordination number of the cubic hole, I didn't give coordination number in the summary tables, but we can look at it here, and what you see is that this center one here is surrounded by 8 now. So another trend you'll see if we put coordination number into that table, which I guess I should probably go back and do eventually, is that the coordination numbers of the holes tracks with the relative size. So the smaller the hole, the smaller the coordination number, the less ions you can surround it with. The larger holes have larger coordination numbers. So we've seen that octahedral was 6, cubic hole is 8, so as you increase the size of the hole, you're able to surround it with more ions. The coordination number then gets bigger. All right, the last one we'll do as sort of an example structure is zinc sulfide. So zinc sulfide has a formula ZnS. Zinc forms 2 plus cations, sulfur forms 2 minus anions, so it's again a 1-to-1 compound. So let's look at the ionic radii that we have for this compound. We didn't talk a lot about periodic trends for transition metals, but zinc 2 plus is a 2 plus cation, so it's pretty small. Every time we remove an electron, we tend to get smaller. So this has a 60 picometer radius. Sulfide is very similar to chloride. They're isoelectronic. So we saw that chloride was 181. Sulfide is just a little bit bigger than that, 184. So very similar in size to chloride. Okay, so those are the sizes that we get for the 2 ions, and again we have to take the ratio of those 2 to figure out which holes are filled. So smaller divided by the bigger one gives us a ratio of 0.33 or thereabouts. And as we saw, if this radius ratio is between 0.225 up to 0.414, or in other words, if it's smaller than 0.414, because we don't have any holes that are smaller than the tetrahedral holes, in this situation you're going to fill tetrahedral holes. So when the positively charged cation is this much smaller than the anion, you have to fill the tetrahedral holes to be able to fit them in there. Okay? And then we have to figure out how many of these are filled. So let's again think about the number of each ion we have. So in this structure, we're showing sulfur in yellow, zinc in, is that gray or purple? I can't tell, I guess purple. Yeah, it's purple to you guys at least. So we have this structure here. Let's figure out how many of the tetrahedral holes we need to fill. So our sulfur ions occupy a face-centered cubic arrangement, as they always will be the case when you're occupying tetrahedral holes. So our larger ion occupies the face-centered cube, and as we saw already when we counted this before, that means we have 4 of those anions. So in our unit cell, we have 4 S2 minuses when all of the corners and all the faces are occupied. As we saw when we counted tetrahedral holes, we have 8 tetrahedral holes, all of them inside of the unit cell. So if we filled tetrahedral holes, we would actually have 8 zincs if we filled every single one of them. So what this means then is if we want to have the correct ratio of 1 to 1, 1 zinc to 1 sulfur, we're only going to fill half the tetrahedral holes. All right, if we filled every single tetrahedral hole, we would get 1 sulfur to 2 zincs, which is the incorrect ratio. So if we want to have a 1 to 1 ratio, we can only fill half the tetrahedral holes. So we want the formula then would be, if you filled all holes, you would get zinc 8s4, which is wrong. What we actually want to do is just fill half the tetrahedral holes so that we get zinc 4s4, which comes out to the correct empirical formula of ZnS, 1 zinc, 1 sulfide. So we only fill half the tetrahedral holes in this case, and that's what we're showing here. We see that we have tetrahedral holes filled there and there, there and there, but the ones that are opposite from those are not filled. So we have an empty one there, an empty one sort of there, and then on top we have an empty one in the front and another empty one in the back. So we have still 4 more tetrahedral holes in this case that are not occupied at all to get the correct ratio. All right? So I'll erase those so I don't confuse anybody that looks at these after the fact. But we only have half the tetrahedral holes filled to get this 1 to 1 ratio. And then if we think about the coordination number, again, the word tetrahedral sort of gives it away. The coordination number would be, each one of these is surrounded by 4 others that are nearest neighbors. And we know from our studies of VSEPR that the tetrahedral geometry corresponds to 4 electron groups, or 4 things surrounding the central atom. So I accidentally reproduced this slide, so I'm not going to do it again. But what I do want to go back to real quick, because I should have included it, is the coordination number part of this. So just for completeness, let's talk about the coordination number of each of these. And the name of them, in most cases, gives it away. So tetrahedral hole, coordination number of 4. Octahedral hole is a coordination number of 6, meaning 6 ions surround it when you're in an octahedral hole. Cubic hole, coordination number of 8. All right, so we clearly see the trend. As the size of the hole increases, the coordination number also increases from 4 to 6 to 8. All right, so we defined coordination number last time for metallic structures, and it also means the same thing for ionic compounds. It's the number of nearest neighbors, the number that come in close contact with them. All right, any questions so far? All right, the last thing we're going to do before getting on to the activities we have left in the other class is just a few sample problems. So these will give you an idea then of the types of problems that we're going to have. So, as I said, we're not going to have you memorize all these different structure types. We're not going to have you, try to tell us off the top of your head what's the crystal structure of calcium fluoride or all these different things. But if we give you some information about it, we want you to be able to make predictions about the structure and talk about, which holes are filled, how many of them are filled, and so on. All right, so let's talk about the compound calcium fluoride. So if we're going to think about this, the first thing we need to think about is what's the formula of this compound. We want to know what's the ratio of cations to anions in this structure. So just to go way back in time, if we look at calcium fluoride, calcium is in group 2, so it's going to form a 2 plus cation. Fluorine is in group 7, so it gains 1 electron to form a 1 minus anion. So what should hopefully be clear by this point is that the correct formula for calcium fluoride is going to be CaF2. 2 minus 1 fluorides to balance the plus 2 charge that you have on calcium. So we need to know the formula if we're going to evaluate anything about the structure. And so in this question, what we're told is that the cations in this case occupy a face-centered cubic array. So a little bit different than we normally see. In this case, it's the cations that are in the FCC, but we're telling you that directly. If the anions fill the tetrahedral holes, how many of the tetrahedral holes must be filled? All right. So let's first think about how many cations we have, because we know the cations are in the face-centered cubic arrangement. So reviewing the counting rules that we've seen many times before, in a face-centered cubic structure, as again FCC as we abbreviate it, we have 8 corners filled that we count as 1/8 each. And then we have the 6 faces as well, which we count as a half. So that means in our unit cell we're going to have 4 calcium 2 plus ions if they're occupying all of the face-centered cubic positions. So anytime you occupy face-centered cubic, you have 4 atoms or 4 ions of that type. And then we want to think about how many tetrahedral holes there are in total. So if you can internalize the information that's on that summary table that we built, that's going to be the most important thing for you to learn in this. and we would know that then there's 8 tetrahedral holes. All right? So if we have 4 calciums in the structure, and the correct ratio is 1 to 2, that means we have to have 8 fluorines to give a 1 to 2 ratio. And so what this means is that we need to fill all 8 of the tetrahedral holes. Okay? So all 8 have to be filled to be able to get the correct ratio of 1 cation to 2 anions. If only half of them were filled, it would be a 1 to 1 ratio. This time we want a 1 to 2 ratio, so we need them all to be filled. That gives us 4 calciums, 8 fluorines for a correct ratio of 1 to 2. All right, so any questions on that? All right, the last example that I'll do is this one here. So we have the compound lithium boride, which is a binary ionic compound of lithium and boron. So we have some ratio of lithium to boron. In this structure, the boron ions occupy the positions of a face-centered cubic lattice. If the lithium ions occupy all of the octahedral and tetrahedral holes, what is the formula? So in this case, we're telling you which positions are occupied. We're telling you that the boron ions are on the face-centered cubic positions, and then the lithium ions are filling both octahedral and tetrahedral holes. This is a rare case of an example where you fill both holes. And so if all of those are filled, what's going to be the correct formula then for this compound? So if we think about how many borons there are, it occupies the face-centered cubic positions, and as we've seen many times already, that means we have 4 of them. Okay, 8 corners plus the 6 faces gives us a net of 4. We just counted that in the last one. It's still the same FCC arrangement. Now let's think about how many lithiums there are. So we said that the lithium occupies both the octahedral and the tetrahedral holes. So we see that if we remember this, there's 4 octahedral holes, 6 in the faces and 12 on the edges and 1 in the center. That's a total of 4. And we said that there's 8 tetrahedral holes. So if we're filling both of those, all 4 octahedral holes, all 8 tetrahedral holes, that would mean we have 12 of our lithium cations. Okay? We have 4 borons, we have 12 lithiums. So we get Li12B4, and then like any ionic compound, we want to reduce it to the smallest ratio. So that's Li3B, lithium boride. All right, so this was an example where we gave you the structure and asked you to then fill in what the formula would be by working backwards. All right, the people that are doing the evaluations are not coming for another 10 minutes or 15 minutes or so I don't think I can milk a bonus quiz that long. So what I'm going to do is there's one thing that I meant to cover earlier that I haven't, so I'm going to, if you just give me a quick minute, I'm going to do that. So let me try to figure out how to, I think I can add a page here if I get out of this view. Edit, page, insert page. Okay. All right, so what I want to cover, one thing that I want to cover, I think most of you figured this out by doing the homework, but I've gotten some questions on it, and I realized that I neglected from covering it in class. So I just want to spend a couple minutes on, yep, so we're not done yet. So you may have seen in some homework questions, we would talk about, this is back from chapter 8. This will be important for the exam, so you might want to listen up. We will cover it in the review, but you probably saw in some of the homework questions, we would say that you have a gas at STP. So that abbreviation STP that you probably saw, which I think most of you did, put a little bit of effort and figured out yourself. But I just want to make sure I cover what that means. So STP means standard temperature and pressure. STP. Now keep in mind that this only applies to gases, to ideal gases. There's another thing that gets confused with this sometimes called standard conditions. We talked about standard states of the elements a little bit earlier. That's a different story. So standard states applies to 25 degrees Celsius and some other things that you'll worry about more in Chem 2. But when we're talking about ideal gases, if we use the terminology STP, or standard temperature and pressure, what that specifically refers to is the temperature is equal to 273 Kelvin, or 0 degrees Celsius, and the pressure is exactly equal to 1 atmosphere. Okay? So whenever you see STP, you know then what the temperature and the pressure are, 1 atmosphere, 273 Kelvin. And it will be given to you directly. Now there's a relationship that comes out of this. So if we start with PV equals nRT, let's figure out let's figure out what the volume is of 1 mole of gas. Let's assume that we have 1 mole of gas, and we're going to figure out what's the volume at STP. So if n equals 1, the volume is going to be given by nRT over P, just rearranging the ideal gas equation. So if we have 1 mole of an ideal gas, and we're at STP, that means our temperature is 273 Kelvin, and our pressure will be 1 atmosphere. This comes out to the number that some of you are familiar with, 22.4 liters. Okay? So 1 mole of any gas at STP has a volume of 22.4 liters. That can be a helpful relationship if we're doing things like gas stoichiometry, where we're asking you about how much volume of each gas is involved at STP. This relationship of 1 mole being equal to 22.4 liters can be helpful. The reason that I don't try to introduce it too early, and the reason that I don't necessarily suggest you always use it, is people they abuse this relationship. They use it when they shouldn't. So remember that this number here only works when you're at STP. Right? You cannot use this relationship at any other set of conditions. So if the temperature is anything different and or the pressure is anything different than STP, the volume of 1 mole of gas will be something different than 22.4. Okay, so this only works if you're at STP, but it also works for any gas. It doesn't matter what gas you're talking about. 1 mole of any ideal gas will have a volume of 22.4 liters when you're at standard temperature and pressure. But don't abuse that relationship, and if you're worried about abusing it, just don't use it at all. Because if you have PV equals nRT at your disposal, which you always do, you never have to memorize that relationship. This is just sort of a shortcut you can use to circumvent using PV equals nRT every time. All right? So any questions on STP, which some of you probably have seen and hopefully didn't cause too much confusion? All right? And then I guess what we should probably do is just get into the quiz, because it's going to take a little bit of time, because there's actually 2 questions today. All right, so today it's a little bit different than normal. So just by virtue of being here, you will get full credit for the quiz. There's no right or wrong answer on this one, so put whatever answer you want. Now what I'm giving you here is a survey. So what I'm trying to figure out, this is going to potentially help me and future students in the future, is to what extent do you use the textbook, and to what extent do you use other resources in this course, trying to evaluate whether there are alternatives to having a $150 textbook that we require you to have. So we're going to try to get some information. So let me go over some things about this. So you don't have to participate in the survey. As I said, as long as you write your name on the piece of paper, you'll get the credit. However, I would very much appreciate if you do, just to help us with this evaluation process. And if you're concerned about if you're concerned about the survey not being anonymous, you are welcome to just write 2 answers on a blank piece of paper and turn your name in on a separate one. I don't think you should be worried, because this information, I'm not going to use it in any way just to figure out. I just want the statistics, basically. I'm not going to care if you don't use the textbook or not. I'm not going to look at the results and say, well, this student didn't use the textbook, so they get a lower grade. No, that's not what this is about at all. It's just for informational purposes. But like I said, if you're worried about anonymity, you either cannot participate if you choose to, or you can write your answers on a separate piece of paper from your name, so I don't know which answers you put. But you shouldn't be concerned about that, but if you are, that's no problem. All right, so like I said, write your name and ideally your student number on the bonus quiz too, because in this, some of you have the same name, and I know this is the pot calling the kettle black, but some of you have poor handwriting, so having the number there is a nice crutch for me to be able to, to identify you if I can't read your name. So anyway. Please do that. And the other thing is, because I'm in a giving mood today, this has nothing to do with the evaluations you're about to do. if you don't have one of the quiz forms, just write it on any half sheet of paper and that's fine, okay? So if you're, well, yeah, so I didn't think that was that big of a deal because most of you seem like you have them anyway, but if you're short a quiz form and you don't have a close friend you can borrow one from, feel free to just write it on any half sheet. Please make it a half sheet though, because if I have all different size pieces of paper, it's dangerous to carry them back. All right, and then as I said, there's 2 questions on this, and I would really appreciate if you can make it clear which answer is for which question. So either make sure you write them in the correct order, so either answer both questions, don't answer anything. If you just put one answer down, I'm not going to know which question that refers to, so just make it clear. Either write the answers right one after another or put numbers next to them to tell you that this is the first question, second question. Because this is the only 2-question bonus quiz, but like I said, no matter what you put on your paper, you'll get full credit. All right, so the first question here is asking about textbook usage in the course. All right, so take some time, answer it honestly. If there's no right or wrong answer, as I said. And we want to know which of the following, I should stop this, the people